So how do we use the contraction mapping theorem for the proof of existence and uniqueness? We already defined the operator P. We will now define a suitable X and S and the subset S, and we will show that this operator P we already defined is a contraction on S, and then we will use the contraction mapping theorem. So what is this X? So X we will define is a set of all continuous functions from this interval 0 to delta to Rn. Yeah? So the notation for X is C0 from this domain to this codomain Rn. This 0 means that it is required to be just continuous. It could be differentiable, twice differentiable, that is an extra property, but we are asking for all functions that are at least continuous, and hence the 0 appears here. So over what interval it is defined from 0 to delta, the time duration, that delta is to be carefully chosen yet. Now we can ask the question, is X complete with respect to some norm? After all, for the contraction mapping theorem we require a Banach space X. So with which norm is X complete? So we already saw that for a point X in capital X, we saw the sup norm for this space of functions, for this space of continuous functions, we define the sup norm as the maximum as t varies in the interval 0 to delta of the Euclidean norm of x of t. At any time t, x of t is a vector in Rn, and we can take the conventional 2 norm, the Euclidean norm, and this Euclidean norm itself is a function of time, and we will see what is the maximum of that norm function as t varies from 0 to delta, and that is called the sup norm. It is also called the max norm. So we already saw that with respect to this sup norm, this space of continuous functions on this interval to Rn is a complete normed space. The next important property was, the next important requirement was to define the closed subset S. So we take some r greater than 0 and we define the set S of all those continuous functions in this particular set which satisfy the property that x minus x naught, x naught here is actually just a vector, but we also think of it as a function. We will see this in more detail, but the distance from this x naught, the supremum of the distance of this as t varies over the interval 0 to delta is at most r. So we take all those continuous functions which satisfy the sup norm condition and we pick these functions and put them into the set S. How do we choose the value of r for this definition of S? So we have the differential equation f. In the differential equation d by dt x is equal to f of x, we already are given that f is locally Lipschitz at the point x naught, and what is the significance of x naught? X at time t equal to 0 is equal to x naught. So because it is locally Lipschitz, we know there exists a neighborhood B, the ball B centered at x naught and of distance and of radius equal to r. This closed ball, we will very soon define it to be a closed ball. We know that because f is locally Lipschitz at point x naught, there exists such a ball such that the Lipschitz condition holds inside this ball. To say that the Lipschitz condition holds means that for all x1 and x2 inside this ball, this inequality is satisfied. Yeah. So we pick this r from the locally Lipschitz property of the function f. Also this S, the way we have defined, is a closed subset of x. It is a closed subset because of this inequality being a non-strict inequality. Yeah, so notice the less than or equal to r above. For the same reason, we will conveniently choose the ball B x naught comma r as the closed ball. So B x naught comma r is defined to be the set of all x such that the distance from x naught is at most equal to r. Okay, so before we go further in the proof, let us quickly note that B x naught comma r is a closed subset of Rn with the Euclidean norm, and the point x0 is a element of this closed ball. It is in fact the center of this ball. On the other hand, S, the subset S, is a closed subset of x, the space of continuous functions over the interval 0 to delta, and this space x has the sup norm, because we are dealing with two types of norms here, one a norm over Rn, the Euclidean norm, and another a norm over x, the sup norm. Because we are dealing with these two norms, it is very important to be careful about which norm at each place we use the norm function. So, for this subset S, we have this particular function x of t, which is always equal to x naught, always equal meaning as time t varies from 0 to delta, x of t is the constant function, it is equal to x naught. So, this constant function is also an element of the set S. So, what is the meaning of that? The trajectory x of t is always equal to x naught, it remains at x naught for all time t. So, what is the set S? S is a set of trajectories that remain within distance r from the point x naught for the time duration 0 to delta. So, what does the operator do? Operator P do? It takes x, small x in capital X, and gives another function again on the interval 0 to delta. So, hence we see that P is a map from x to x. We now show that in fact P maps S into S for some delta suitably small. Notice that we had delta as some number that was to be chosen yet. So, for delta suitably small, we will show that P maps not just x into x, but in fact S into S. Then we will use the locally Lipschitz property of the function f to show that P is in fact a contraction on S, again for a sufficiently small delta. This we will call delta 2 greater than 0, and once we have these two conditions, delta 1 and delta 2, one which ensures that P maps S into S and another which ensures that P is a contraction on S, we will define the delta to be equal to the minimum of the two, of delta 1 and delta 2, and since delta 1 delta 2 are both positive, the minimum of the two will be a delta that meets the conditions in the theorem. For this particular delta, we will use the contraction mapping theorem. So, the first part of the statement was to show that for delta quite small, Px minus x naught sup norm is less than or equal to R when x is in S. To show this particular inequality will imply that P takes an element x in capital S and gives you a function which is also in capital S. Why does it give a function again in capital S? Because the distance of P of x from x naught, from the constant function x naught in the sup norm is at most R. If we show this, this will ensure that P is a map from S to S. So, in order to show this, notice that P of x of t minus x naught in the 2 norm is equal to this. So, once we take the norm function inside the integral sign, it turns out that this right hand side will become larger. So, this inequality, this norm of integral 0 to t P of x of tau d tau is less than or equal to integral 0 to t of this whole thing inside the brackets. So, notice that we have just subtracted and added f of x naught, and while doing this, this particular quantity can increase because of the triangular inequality. So, now what we will do, we will integrate not just from 0 to t, but 0 to delta 1. After all, t is some number at most delta 1. So, if we integrate this positive quantity up to delta 1, it is only going to become larger. And once we do this, we will also use the Lipschitz property of the function f and replace the first term in the norm with x tau minus x naught times L. Because f is locally Lipschitz at the point x naught, this is satisfied for all x and x naught inside that ball. This other quantity we just leave as it is. So, we have used the locally Lipschitz property of the function f. since x of tau minus x naught is at most equal to r. Why? Because the function x is inside S, hence this particular quantity is at most r. So, we have replaced x of tau minus x naught in the 2 norm by r, that is the maximum distance it can be away from x naught. And the second quantity, because it is integral of a constant, we have removed f of x naught and replaced integral of d tau by delta 1. Finally, we see that this particular quantity which we are integrating, this is also constant, it is not varying as a function of tau, and hence we equated that to delta 1 LR, and after taking delta 1 common, we obtain this expression. So, what have we shown? We have shown that the 2 norm of this particular function at any time t is bounded from above by this quantity, and notice that on the right hand side there is no t. So, for all time t, the left hand side which depends on time t is bounded from above by this particular number which does not depend on t. So, in fact, if we take the supremum of the left hand side, even the supremum will be bounded from above by the same quantity. So, what does this show? That this particular p of x minus x naught in the sup norm is at most equal to this. So, now we will choose delta 1 such that p of x belongs to S. So, if p of x should belongs to S, then choose delta 1 to satisfy delta 1 times LR plus f of x naught 2 norm is at most equal to R. If we choose this delta 1 such that this is satisfied, then we see that p of x minus x naught in the sup norm is bounded from above by R, and hence p of x goes into S. So, we can take any positive delta 1 that is less than or equal to R times R divided by this quantity, and we will then get that p maps S into S. So, we can take delta 1 equal to this. The next important step was to show that p is a contraction on S. So, for some delta 2 greater than 0, which we will carefully choose now, we will show that p is contractive. So, for this purpose, notice that p of x t minus p of y t in 2 norm is equal to the norm of this. From the definition of the operator p, we see that we obtain this, and when we take the norm inside the integral sign, then we get that this is at most equal to this. By using the locally Lipschitz property of the function f inside the ball b of x naught comma r, we see that this quantity is bounded from above by this after taking the L outside this integral sign. Moreover, this particular quantity we have written here is at most equal to this. Why? Because x and y both at any time t, we can take the difference between them in the 2 norm and integrate them, but instead of taking at any time tau, we could also look at the maximum difference between them, and this maximum difference is only going to be larger, and hence we have obtained that this particular inequality is less than or equal to this particular quantity. By replacing the sup norm here, by replacing the 2 norm there with the sup norm here, this quantity can only become larger, and hence this inequality less than or equal to. Finally, this quantity which we are integrating, it is over the interval 0 to t, but we could go ahead and integrate up to delta 2. This quantity, because it is a norm, it cannot be negative, and when we integrate further, instead of only up to time t but up to delta 2, then we see that we get L times delta 2 times sup norm of x minus y. So, here the supremum is being taken as t varies from 0 to delta 2, and here also the sup norm was being taken as t varies from 0 to delta 2. So, what have we obtained? We have obtained that p of x of t minus p of y at time t, the difference norm of that, the 2 norm of that is bounded from above by some number, by some quantity that is independent of time t. and this is true for each time t in the interval 0 to delta 2, and hence we can take the supremum of this quantity. Even the supremum will be bounded from above by the same number, L times delta 2 times sup norm of x minus y. So, finally, we have obtained this inequality, sup norm of px minus py is at most equal to L times delta 2 times sup norm of x minus y. So, this should give us a hint as to how to choose delta 2 so that P is a contraction on S. That was the objective of doing this inequality. So, when would this be a contraction? It would be a contraction if this particular quantity L times delta 2 is strictly less than 1. So, if you set delta 2 times L equal to some number rho, and that number rho is strictly less than 1, then we will obtain that P is a contraction on S. So, finally, we do as follows: choose any rho strictly less than 1 and define delta to be the minimum of these two quantities. So, notice that this we had called as delta 1, the second one we had called as delta 2, and the minimum of these two quantities, when we take that as delta, it will ensure both. It will ensure that P is a map from S to S, and it will ensure that P is a contraction. And once these two are guaranteed by the contraction mapping theorem, we know that there exists a fixed point in S for the operator P, and moreover there exists a unique fixed point for this operator P, unique fixed point inside the subset S. So, this proof has two parts. So, this completes the proof. Just a small discussion about the proof. It has two parts, one about the existence and one about uniqueness. So, notice that both come together with the contraction mapping theorem. The contraction mapping principle assures us both existence and uniqueness. But of course, in general, the conditions on F for existence of a solution to the differential equation are different from conditions on F for uniqueness of the solution to the differential equation. These conditions are usually different, and suppose the existence is given, suppose due to some particular property on F, it turns out that we have a solution to the differential equation.